Kia ora and welcome to question 1 of the 2008 Skull Calc exam. In the first question here we have a problem involving areas of hexagons. We move on to part B, which is an optimization question, still with hexagons in it. In this case we're looking at the cell of a bee's honeycomb. And then part C is a related rates question. Okay, so for the first part A, we've got, first of all, to show that the area of a regular hexagon with a side length of s is equal to 3 root 3 over 2s squared, and then hence show the total area of the hexagonal stack shown is 24 root 3 s squared, which seems a little bit easy for a scholarship question. The first part's okay, but the second part we just have to multiply by how many hexagons are in the stack. First up, let's think about our hexagon here and find a way that we could break it up into easier shapes to work with. We've got a couple of ways we could do this. We could think of splitting it into two triangles and a rectangle, but probably the easiest way to do it is to think about it from the center outwards. It's a regular shape, therefore we can split it into 6 regular triangles, all with an angle of 60 degrees. If you know your rules for interior angles of shapes, then you could go sides minus 2, n minus 2, all times 180, divided by 6 will give you the interior angles of the hexagon. So in this case, a hexagon's got 6 sides, so we're going 6 minus 2, 4 times 180 over 6, which is 30. So every interior angle there, and when I mean interior angles, I mean this angle there, is equal to 120. And because of symmetry, we can say that these are actually equilateral triangles. So we need to find the area of 6 equilateral triangles to find the area of a hexagon. The side length of the hexagon is s, meaning that these two sides here are s. We use either right angle trig or level 2 trigonometry. Probably quicker to do that and go area of a triangle is half AB sine C. A and B are both S in this case. Okay, that there, A and B, and the C is the angle between A and B. So we go half times S squared times the sine of 60 degrees. Sine of 60 is has a nice exact form because it's just from a special triangle. 60 degrees. This is on the formula sheet for calculus, but 60 degrees there forms a special triangle where this side is root 3, that side's 1, and that's 2. So the sine of 60 opposite over hypotenuse is root 3 over 2. So we've got a half s squared times root 3 over 2, and therefore the area of the hexagon is going to be 6 times that. 6 times root 3 s squared all over 4, and 6 over 4, 3 over 2, root 3 s squared, which is what we were trying to prove, hence show the total area of the hexagonal stack is 24 root 3s squared. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hexagons. Area of the stack equals 16 times 3 over 2 root 3s squared. And 16 over 2, there's 8, so we've got 24. When we put the 3 there, 24 root 3s squared. Done. Okay, second part. Although a single cell of a bee's honeycomb has a hexagonal base, it is not a hexagonal prism. The complete cell more commonly has the shape shown in figure 2, and the surface area of this cell is given by the following formula. We don't have to derive it, thank goodness. But we are told that H and S are, H there's the height of the honeycomb, S is still the side length. Oh, they tell us down there that it's an equilateral triangle. which interestingly we used in the first part without it telling us. So you can see there, so S, there's an equilateral triangle there, and it doesn't tell us that the base is a regular hexagon, but we're given the surface area formula, so we don't need to know that. Keeping H and S fixed, so the hexagon's side length and the height of the honeycomb cell doesn't change, but theta is able to change. For what angle theta is the surface area a minimum, and we don't need to prove it's a minimum. Okay, so we just need to differentiate this formula. Okay, area equals 6hs, that term there is going to disappear when we differentiate it, plus 3 over 2s squared, that's a constant. I'm just going to write minus cosine over sine, this part here, just write that as minus cotan, because it makes it quicker to differentiate. Cosine divided by sine is cotan. So we've got minus cotan theta, and then the last term, root 3 over sine theta. I can bring the sine theta up as sine theta to the power of -1, or I can use the fact that when I divide by sine, dividing by sine is the same as the cosec function. So root 3 over sine is the same as root 3 cosec theta. Okay, now there's the function we need to differentiate. We're finding the minimum surface area, so actually, rather than be lazy and write a dash, I'm going to write dA d theta to remind me that I'm differentiating with respect to that being the only variable in the question. The other two variables are treated as constants. 6hs is fixed, so it differentiates to nothing. 3 over 2s squared can sit in the front, and then we need to differentiate minus cotan and root 3 cosec theta. So this is just really an achieved question. We look at the formula sheet. Cotan differentiates to minus cosec squared, so negative cotan differentiates to cosec squared theta, and cosec differentiates to minus cosec cotan, so we've got minus root 3 cosec cotan theta, and that's going to equal to 0 for a minimum or a maximum, but the question said we didn't need to prove that. Solving this equal to 0 is equivalent to solving cosec squared theta equals root 3 cosec theta cotan theta. We can divide both sides by cosec theta here. I'm just going to make a note of that in a different color. If I divide both sides by cosec theta, it's all good to do that because cosec theta does not equal 0. Remember that cosec theta is 1 over sine of theta, and that fraction can never equal 0. It's got a 1 in the numerator. So dividing both sides by cosec squared theta will cancel off one on the left-hand side and that one on the right-hand side. So we've got cosec theta equals root 3 cotan theta. And how do we solve this when we've got a mixture of trig functions? Well, we can convert it back into sines and cosines. So cosec 1 over sine theta, cotan root 3 times cosine theta over sine theta. Multiply both sides by sine theta, cancels off those factors, and we're left with solving cosine theta equals 1 over the square root of 3. Now this problem has an infinite number of solutions to it, but I imagine we're just looking for the acute angle. Looking at the picture here, theta looks like an acute angle. If we make it a wider angle than that, the surface area looks like it would increase. Okay, so just solving this by taking the cosine inverse of 1 over root 3, using the calculator to get an approximation for that is approximately 54.7 degrees. If it asked us to find or show that we've got a minimum, we would need to go back to our first derivative and try a value of theta slightly above and slightly below the answer and see that the gradient changes sign and determine whether it's going down then up or up then down. Or the second derivative test if you wanted to. Okay, part C. Another cell is described in part B has S not fixed, but increasing at a rate proportional to sine of theta. So this is a related rates question. S is no longer fixed, but we know that ds dt, the rate that S changes, is some number k, which is our proportionality constant, times the sine of theta. So as theta increases, theta being the angle at the top of the honeycomb, as it increases, sine of theta increases, and therefore the rate that S changes increases up to a point, because when theta gets to pi over 2, 90 degrees, sine starts decreasing, so the rate that S changes starts decreasing. And let's not consider what happens when theta gets above 180 degrees, because the question says, fortunately, we just have to consider between 0 and 90. But if theta did get over 180 degrees, the sine function is now negative, and therefore S is decreasing. Okay, between 0 and pi over 2, S is always increasing, and the rate is getting bigger. Between 90 and 180 degrees, S is still increasing, but the rate is getting smaller. But we're only going between 0 and 90, or 0 and pi over 2. Okay, the rate is equal to root 2, this rate, so ds dt is equal to the square root of 2 when theta is pi over 4. Well, that's quite a nice piece of information, because straight away that gives us what the k value is. Sine of pi over 4 is another special angle. Pi over 4 is a 45 degree angle. 1 square root 2. So sine of pi over 4 is 1 over square root 2. And therefore k is equal to 2 by cross multiplying. Okay, what are we asked? Keeping h fixed, so h is still staying as a constant. At what rate is the surface area decreasing when theta is equal to the value found in part B above? Okay, so we need to keep in mind that theta, for this question, right at the end, we're going to make it 54.7 degrees, or probably better, we're going to remember that the cosine of theta is 1 over root 3 when the angle is 54.7 degrees. So keep that in mind for substitution at the end. Okay, we start off with the same area formula. So I'm going to go back to this dude here and just copy it. Actually, yeah, I will copy that. I can't copy the derivative because I treated S as a constant, but now we know it's not. Okay, so here's our area formula, and the question is saying at what rate is this decreasing? So dA dt is what we're wanting to find. When theta is equal to 54.7 degrees, which is the same as cosine theta is 1 over root 3. Okay, so to find this rate, we're going to use the fact that we know what ds dt is. Okay, this is a pretty typical merit level question. dA dt is going to be equal to dA over ds multiplied by ds dt. So I want to differentiate our function with respect to s. The problem is there's still that theta variable in there. The only one we can treat as a constant is the h. So I want to split this up further if I can. dA dt is equal to dA d theta multiplied by d theta ds multiplied by ds dt. Is that going to help? No, because I don't know how s and theta relate, so I can't find d theta ds. And I also don't have a in terms of theta only. Can I do that? No. Okay, so this exam here, this 2008 exam, was set back when implicit differentiation was a part of level 3 calculus. It's no longer in the level 3 differentiation standard, but it appears in scholarship quite often. Implicit differentiation is just an application of the chain rule, and so we're going to use it to solve this problem. So bear in mind, I do know what ds dt is. Okay, I've already found that formula. It's k sine theta where k is 2. So I've got dA dt is equal to some derivative I need to find multiplied by 2 sine of theta. And dA ds, okay, how do I differentiate this function up the top with respect to s only? Okay, well the first term is pretty straightforward. Okay, the first term is 6hs, h is a constant. So when we differentiate that with respect to s, we just get 6h. But the second term is a product of two things. Now, we can't treat the 3 over 2s squared as a constant. It's a function in terms of s. And then the second expression in the brackets is just in terms of theta. So to differentiate that, I need to use the product rule. And I'll call this first term here f, and this whole second term here equal to g. So to differentiate this with respect to s, I need to differentiate f, then times by g, and then differentiate g and times by f. Okay, so the derivative of f, 3 over 2s squared differentiates to 3s, multiplied by the brackets, and then differentiate the brackets with respect to s, which I'm going to just write like this because I will explain it in a sec. All times by the first term, not differentiated. Okay, so that's pretty much all done except for the fact I need to differentiate that bracket term with respect to s. And how do I go about doing that? Implicit differentiation says if you want to differentiate something with respect to another variable, and you need to know that theta and s do relate, so theta will depend on s. It's just we don't see how it depends on s. To find this dude here, we're going to differentiate it with respect to theta instead. And then we're going to multiply it by d theta ds. And based on how our related rates and chain rule and all that sort of stuff works, those thetas there cancel and we get dds, the derivative with respect to s. Okay. So dA dt is equal to, I'm going to put this in big giant brackets now because this whole thing is dA ds. Alrighty, dA ds is 6h plus 3s times that bracket. Something's going to be cool about that bracket in a sec. I've just noticed something. Okay, plus the green stuff, which is the derivative with respect to theta of that bracket. So we need to go back and go, how do we differentiate minus cotan and root 3 cosec? We've already done that. Cosec squared for the first term and minus root 3 cosec cotan. Oopsies, I've turned something into an x because I'm reading the formula sheet. Cosec cotan multiplied by d theta ds, which is something I don't actually know because, like I was saying earlier, I don't know how theta and s relate, which seems like we've got an unsolvable problem here, and also multiplied by the 3 over 2s squared. Okay, that. Unfortunately, I'm going on to the next page here. You can do that in an exam if you want, just work on a double spread. Just be careful if you do that you don't write in the margins, they cancel. Actually, so it's probably not best to go on a double spread, they do cut the margins. What else have we got? Oh, all of that is dA ds multiplied by 2 sine theta. Alrighty. Like I was saying, we don't know what d theta ds is, but fortunately, for this particular value of theta, for theta equals 54.7 degrees, it turns out that this stuff here in yellow is equal to 0. So if we go back to that original problem where we optimized the surface area, we solved this bracket here equal to 0. Cosec squared minus root 3 cosec cotan. Okay, so that whole thing's equal to 0, meaning we don't need d theta ds. You'd still have to put that there to show that you know how to differentiate, but the whole thing's going to go to 0. Therefore, equals 0. dA dt equals 6h plus 3s minus cotan theta plus root 3 cosec theta. As the only term in that bracket that still lives to see another day, multiplied by 2 sine of theta. Okay, now we can distribute the 2 sine theta through the brackets. So we've got 12h sine theta, and then 6s, which sounds awfully like success, and we're near the end here. Cotan is cosine over sine, and we've got a sine on the outside, so we're just going to get negative cosine of theta, and then root 3 cosec is the same as 1 over sine, so the sines will cancel, and we're just left with root 3. Okay, so that's me distributing the 2 sine theta through the brackets. What I mean by that is I've times both things in the brackets by the 2 sine theta, kind of like expanding brackets. And then lastly, we need to go and substitute theta equals 54.7 in again, or remember I said that that's equivalent to just remembering that cosine theta is equal to 1 over root 3. Drawing a triangle for that, it's a third right angle triangle I've drawn in this video. Cosine theta equals 1 over root 3 is the same as saying that is 1 and that is root 3, and therefore the opposite side can be found using Pythagoras as root 2, which means that we can find the sine of theta in this case as well. The sine of theta will be equal to root 2 over root 3, and that allows us to substitute into here and into there. Rather than finding theta, which we know is 54.7, we can just substitute cosine and sine theta in. Okay, so the final answer to the problem is 12h times root 2 over root 3 plus 6s times negative 1 over root 3 plus root 3. And we can pull out the 1 over root 3 if we wanted to. So we've got 12 root 2 h, and then we have 6, no we don't, we have minus 6s. What's that last term? It doesn't have a root 3 in the denominator, but I can give it one. But timesing top and bottom by root 3. So root 3 times root 3, there's 3, and then we've also got a 6 out the front, so 18s. Okay, then we've got some like terms to tidy it up and find the final expression, but I imagine the final mark would be for any of these last sort of 3 lines. An interesting thing there is that h and s are both positive. It's the height and the side length of the hexagon and the base. So we've actually just found that for this value of theta, the area is increasing, and the question asked us to find out what rate the surface area was decreasing. So it's actually a mistake in the exam, and it's kind of reflected in the schedule. It says the negative sign is not needed, but the problem's actually wrong. We've got dA dt as a positive number. Okay, that's the solution to the problem, and we'll catch you in the next video.